Hi, my name's John Doyle and I'm a technical manager at Solid Solutions. I've worked in the CAD industry for over 25 years and in recent times have specialised in the simulation tools. The CAD industry actually goes back much further than my career, with the very first development started by Patrick Hanratty, known as the father of CAD-CAM, right back in 1952. This video is showing a demonstration of the first interactive CAD program, which was called Sketchpad. Developed at MIT in 1963, it used a light pen and an oscilloscope to create and edit geometry. The 1970s saw the start of 3D CAD, and in 1977 the release of CATIA, which stands for Computer-Aided Three-Dimensional Interactive Application. It started as an in-house development by the aircraft manufacturer Dassault to develop their Mirage fighter jet, and was later adopted by aerospace, automotive and shipbuilding industries amongst others. The widespread adoption of CAD started in the 80s with the release of AutoCAD in 1982. However, this was still primarily 2D, and it wasn't until the release of Pro Engineer in 1987 that saw 3D become available to a wider audience. In the 90s, PCs finally became powerful enough to run 3D CAD applications, and in 1995 SOLIDWORKS was released, which was the catalyst for the mainstream adoption of 3D CAD. Today, virtually every product that's manufactured will have been created in 3D CAD. There are free online packages. It's taught in secondary schools. For example, every secondary school in Ireland teaches children SOLIDWORKS. There's even software aimed at primary school aged kids. So 3D CAD has undoubtedly made it to the mainstream. But can we say the same for virtual testing or simulation software? Despite the fact that the development of FEA running on computers also dates back to the 60s, it's not yet become as widespread as 3D CAD. So what are the possible reasons why this is the case? Is it cost, ease of use, a lack of integration with existing design tools, or the perception that there's a need to employ an expert? In this video, we'll look at how SOLIDWORKS simulation solutions can address some of these concerns, and hopefully try to demystify simulation. The simulation products cover a range of different disciplines, from structural simulation, which typically looks at stresses and displacements in parts and assemblies under a range of different conditions, fluid dynamics, which looks at how models interact with liquids and gases, plastics to simulate the injection moulding process, and motion, which looks at the physics of moving assemblies. In this video, we're going to concentrate on the two most common areas of structural simulation and fluid dynamics. All of these tools share the same core values in that they're easy to use and integrated within the design process. They're also able to work with each other, so we might use flow to calculate pressures or motion to calculate forces, which are then applied as loads in a structural simulation. Within structural, we have a wide range of different study types. Our loads can be static or dynamic. The material behaviour can be assumed to be linear like a metal or non-linear like rubber. We can also look at resonance, vibration, drop tests and many other scenarios. We can then optimise designs either through changing dimensions or changing the shape. We have customers using these tools in all industry sectors, from heavy industrial applications through to consumer goods. One of these customers is Renthal, who are a global leader in the design and manufacture of components for motorbikes, cycles and all-terrain vehicles. They started manufacturing handlebars for motorbikes 50 years ago, and more recently in 2010 expanded into cycling products. Their components are now used at the very top of world sport, with over 200 motorsport world titles and 11 already in cycling. All bikes and their components have to comply with the ISO standard 4210, which stipulates the test that parts must pass. One such test that Renthal needed to simulate was the fatigue testing of handlebars and stems, as shown in this video. Being able to virtually simulate this test not only alleviates the time and costs involved in machining prototypes, but also means they could produce a better design that's stiffer and lighter with confidence that it would pass the test first time. In this example, we're going to replicate those tests using a BMX bike stem. The standard has different categories for different types of bikes, so we'll use the highest load for BMX. But it's still quite conservative, so we'll double the number of cycles and increase the loads by 50%. The test has two different elements: in-phase loading, where both sides are forced up and down together, or antiphase, where one is forced down and the other up. These are run as 200,000 cycles of each. We typically start with a static study, and as we're only interested in the stem, we have replaced the handlebars with a test bar. Directly inside of the design environment, we can create our simulation study, which presents us with a list of items to consider. First, we have the material, which has already been applied. Then we have the interaction between the various components, which will change from being bonded to allow the parts to slide and separate from each other. As we aren't including the steerer tube, we'll simply fix the back of the stem. We then apply our loads, and we'll start with the in-phase test with two forces acting in the same direction. Finally, we can include the effect of the bolts, including a preload as a torque, and then we simply mesh and solve our study. The default result plots are exaggerated to clearly show how the parts deflect, which we can change if desired. The initial results show us the stresses in the various parts. To understand the implications of those stresses, we can look at the factor of safety, and by giving the areas that are carrying less load a different colour, it gives us some insight into the material we could safely remove if we wanted to make the part lighter without impacting the strength. As we're always in SOLIDWORKS, we can make quick changes and see how the factor of safety is affected. Because we've removed geometry that wasn't contributing to the strength, we can quickly reduce the weight without compromising the stiffness. Having finalised our design, we'll now move on to the fatigue test. With the inclusion of the bolts, which are a dead load, so not loosened and tightened with every cycle, we need to start with all four cases: up, down, clockwise and anti-clockwise. In the fatigue study, we can then alternate between two of these studies for each test, applying 200,000 cycles of each. The results then show us how much damage these cycles will have caused. The values represent a percentage of the life that the tests have consumed. In this case, 3% shows that our design would easily survive those 400,000 cycles, and if we continued for many more, where the cracks are likely to develop. That has shown how simulation can help validate and also guide the design of an existing component, but it can also create brand new geometry through topological optimization. Here we're trying to create a brand new design for a mountain bike stem. We've built in some basic parameters such as an 80mm reach and a 6° rise, along with locations for clamping around the tube and bars. Other than that, we've just modelled a maximum space envelope. We can then apply all four load cases from the previous example. We want to produce a shape with the maximum stiffness to weight ratio, and can also include some constraints such as symmetry and retaining some geometry around the clamps. The results can be quite striking and very different from conventional designs. We can smooth this result and potentially create a part directly using additive manufacturing, or use it as a graphical guide to create a brand new optimal design. We'll now move on to SOLIDWORKS Flow Simulation, which is a general purpose fluid dynamics application that can solve the majority of fluid related problems. They can be internal, like fluid flowing through a flow control device, or external, like drag on a vehicle or convection from a hot surface. It covers all modes of heat transfer. We can simulate how fluids mix, or more complex problems like rotating geometry, free surfaces like water filling or sloshing in a tank, or highly viscous liquids like blood or oil. Flow simulation is again used in a wide variety of industries. One of the fastest growing areas is in electronics. As devices become more powerful and at the same time smaller, the challenge of keeping them cool is increasingly difficult. One example is Name Audio, the British hi-fi manufacturer. They were founded in 1973 by Julian Verica, a racing driver, entrepreneur and self-taught engineer. Dissatisfied with the quality of his home audio system, he decided to build his own. Name have since gone on to win numerous Queen's Awards and have built a reputation for quality. In 2014, they launched their groundbreaking statement amplifier. Using fans to keep electronics cool can have a detrimental impact on sound quality, so they use flow simulation to ensure that the electronics could be kept cool without using the fans in all but the most extreme conditions. Due to the costly components, building prototypes was very expensive and time-consuming, so flow simulation was able to ensure that they got the design right first time. We'll use this small electronics device to look at how we can use flow simulation to predict and visualize the fluid and thermal behavior inside this assembly. We'll look at having fans inside the box or directly mounted to the case, and whether we can improve the performance of the heatsink. Again, all of the setup is done inside SOLIDWORKS, which starts by defining the air inlets. If there are slots or hole patterns on the vents, you can easily account for these without the need for the geometric complexity, reducing computation time. You just need to specify a couple of parameters for the hole pattern. The fans can be specified from a large built-in commercial library or specified manually. Heat sources for the electronics components are specified. Flow also includes the ability to accurately model semiconductor heat transfer, such as for this CPU. It provides a wide range of visualization tools to gain insight into the fluid behavior inside the model. Section plots allow you to look at a cross-section of the model at any location and select for a wide range of characteristics such as velocity, pressure or temperature. A surface plot on the heatsink provides a clear view of the temperature distribution, making it easy to identify uneven cooling and potential hotspots. ISO surfaces are used to show the result of the same magnitude in the design, such as air temperature. You can also show numerous values at the same time, and by making them transparent, it's a great way of visualizing the flow behavior in 3D throughout the whole model. Flow trajectories are another great way of visualizing the flow in 3D, allowing you to see far more than you would in any real experiment. With the ability to animate results and interact with the model, you gain great understanding on product performance. It's sometimes difficult to understand how heat moves around in an assembly. The heat flux plot can show us what is happening visually. We can look at the whole model, or just select certain parts, in this case the main CPU. We can see that a tiny amount of the heat is convected directly, 2.7 watts goes into the PCB and the majority through the heatsink and out into the air. The Compare tool allows us to easily compare the different design concepts and select the best option to move forward with. You can select from both graphical and numerical results, which we can then compare side by side. It then loads each result set, captures the desired information and collates it into images and tables for quick and easy review. Switching to the external fans configuration, we can see that the recirculation has been eliminated and temperatures have dropped. If we needed to further reduce the temperature on the main chip, we could look at improving the performance of the heatsink. And just like structural simulation, flow can also drive the geometry through parametric optimization. We've taken the chip and heatsink in isolation to speed up the calculations. Using the Design of Experiments tool, we can specify a number of parameters to vary. Here we've chosen the number and thickness of the fins. Select the goal we want to optimize, in this case minimizing the temperature of the chip, and then simply specify the number of experiments we'd like to run. From those results, flow simulation can predict what the optimal values would be. We can also visualize the results on a 3D surface, as we might be able to identify an alternative result that's nearly as good, but cheaper to manufacture. Conventional thinking would suggest we just need to maximize the surface area, but if we make the channels too narrow, the flow velocity is reducing, preventing the heat from being moved. This plot shows us where the sweet spots are with the best compromise between those parameters. We've seen how we can solve a wide range of relatively complex problems simply inside of the SOLIDWORKS environment, but occasionally there are challenges that go beyond its capabilities. In those circumstances, we now have a solution that allows us to use the most capable simulation tool available directly from within SOLIDWORKS, and crucially maintain links to the CAD geometry should it change. It's called Simulation Professional Engineer and is built on Simulia, an incredibly powerful, robust and fast simulation solver. In this example, we want to study a very large compression of a complex nonlinear material. We can do our setup in SOLIDWORKS and then transfer the geometry and boundary conditions directly to Simulia. We have access to more material models. Here we'll choose a hyperfoam. We could use the mesh from SOLIDWORKS, but we might have more success with a different type of element. So we'll swap the foam and plate to a hex mesh. With those changes quickly made, we can now run the simulation. We can choose to run it locally, but also have access to more computing power in the cloud if we need faster results. And very quickly, Simulia is able to complete the compression of this foam. If we were to change the geometry back in SOLIDWORKS, we could directly update the geometry and just rerun the simulation. In conclusion, we've seen how SOLIDWORKS simulation tools can solve a wide range of design problems. Being integrated in the design environment makes it familiar and easy to use, and provides insight into the implications of design changes, or alternatively drive the design through optimization. We then saw that if we have extremely complex problems that exceed the capabilities of SOLIDWORKS simulation, that we still have an integrated and easy to use alternative. I hope that I've demonstrated that simulation tools can become an integrated part of the design process as we move towards wider adoption, and have helped to demystify simulation.